Okay, let's jump right into this explainer and actually demystify the machine learning prediction pipeline. We hear terms like algorithms and models thrown around literally all the time, but how do they actually connect together to solve real problems? Well, today, we're going to treat the entire machine learning process like a literal factory assembly line. My goal here is to give you a really crisp, big picture overview of the specific types of algorithms we use at every single step of this problem-solving factory. This is our foundational blueprint, right? Because later, in upcoming explainers, we're going to dive super deep into the code for each of these areas. But first, we really have to understand the overall flow.
So let's look at how this builds our chronological journey. We are following a dataset linearly, straight from the raw, messy input over on the left, all the way to a highly accurate, finalized prediction on the right. And we're doing this across 5 very distinct, interconnected stages. Everything absolutely has to happen in order here, because if one station on this assembly line fails, well, the final product fails.
Here is our roadmap for today. We're looking at data preparation, core prediction, regularization guardrails, ensemble boosting, and finally, continuous optimization. Let's head right out onto the factory floor.
Stage 1. Data preparation. Sorting the raw materials.
Look, before we can even think about building our engine, we have to deal with reality. And reality is that raw data is incredibly messy. It's full of noise, it's bloated, it's redundant. Fun fact here, data scientists actually spend about 80% of their time just doing this step, basically sweeping the factory floor, and the other 20% complaining about it. We absolutely must compress and organize all these redundancies before our core model can even begin processing anything.
To do this efficiently, we bring in our first set of specialized algorithms. For example, principal component analysis, or PCA, is just amazing for compression. It takes datasets with thousands of columns and squeezes them way down while keeping the key patterns intact. Then you've got t-SNE, or UMAP, which are phenomenal for mapping really complex data down to simple 2D or 3D planes. And if materials are missing, we use the KNN Imputer. It literally looks at the surrounding data and automatically fills in the blanks based on its closest neighbors.
Stage 2. Core prediction, the mathematical engine.
Okay, so with beautifully clean materials in hand, we officially enter the engine building phase. This stage acts as the central mathematical brain of the whole operation. It takes all that perfectly prepped data we just talked about, actively searches for relationships, draws decision boundaries, and actually spits out the predictions we're looking for.
So, what tools actually build this engine? We generally rely on 3 main types. First up, linear models, like logistic regression. These literally draw a straight line or a plane right through the data to separate it. Second, tree-based models, like decision trees. Imagine a massive flowchart splitting your data step by step using simple if-then rules. And third, distance-based models, like k-nearest neighbors. This classifies unknown data simply by looking at how close it sits to known points. It's essentially saying, tell me who your neighbors are and I'll tell you exactly who you are.
Stage 3. Regularization guardrails, preventing overfitting.
Once that prediction engine is humming along, we absolutely have to install safety measures to protect against a massive danger in machine learning: overfitting. Overfitting is exactly like a student perfectly memorizing a practice test, but then totally failing the actual exam because they didn't learn the core concepts, right? They just memorized the specific questions. To prevent that, our model needs strict mathematical penalties.
We apply these penalties using 3 primary guardrail algorithms. First is ridge regression. It looks for overly confident data points and mathematically shrinks their impact just to smooth things out. Second is lasso regression. And lasso is ruthless. It identifies completely useless features and entirely eliminates them by forcing their mathematical weights to absolute 0. It literally cleans house. And finally, elastic net, which is a brilliant algorithm that perfectly balances the penalties of both ridge and lasso for really complex datasets.
Stage 4. Ensemble boosting, the multiplier.
Now, with our guardrailed engine ready to go, why stop at just one? In modern machine learning, we don't. Algorithms like random forest don't just run one model. They run hundreds of independent decision trees simultaneously and then average their votes together. We're basically creating a massive, highly accurate committee of quality control.
We achieve this awesome multiplier effect through a few different techniques. Bagging runs all those models at the exact same time and averages the votes. It's the ultimate democratic process. Then there's boosting, using powerhouse algorithms like XGBoost, which trains trees sequentially. Every new tree is forced to focus exclusively on correcting the mistakes of the previous one. And finally, stacking, which uses a master algorithm to seamlessly blend completely different model types together into one super prediction.
Stage 5. Continuous optimization. Tuning under the hood.
Finally, we have our mechanic constantly tuning the inner settings. As this entire cycle runs under the hood, how does the model actually know how to adjust itself? Like, how does it actively minimize mistakes and find the path of absolutely lowest error? Well, it uses optimization algorithms.
The whole thing primarily relies on a concept called gradient descent. I really love this idea. Imagine standing on a literal mountain of mathematical errors. Gradient descent takes iterative, highly calculated steps down that error curve, continuously feeling out the slope until it reaches the very bottom valley, which represents your most accurate weights.
But you don't want to just tumble down the mountain recklessly. So, acting as dynamic speed controllers during this descent, we use algorithms like ATOM and RMS prop. Think of them like your brakes and accelerators. They dynamically speed up or slow down the model's learning rate, ensuring we learn at the absolutely perfect pace and don't accidentally overshoot that bottom valley.
And there you have it, the complete factory floor. From sweeping up the raw data to building the core mathematical engine, installing the guardrails, building a democratic ensemble committee, all the way to continuous optimization right under the hood. You can now see the full forest of how these algorithms conquer complex problems. But the real magic? That happens in the math. So I have to ask, which of these 5 stages are you most eager to dive deep into next? Let me know, because in our upcoming explainers, we are going to start unpacking the actual code behind each and every step.